This lesson is about work done and energy transfers, and by the end of this lesson you should have had a reminder of the definition of work done. You should be able to use the work done equation, and also we're going to be linking kinetic energy and the work done calculations together. So before we start, pause the video and just have a little go at these true or false questions. So work done is measured in newtons is a false statement. Work done is energy transferred, so it's measured in joules. And of course that makes the second statement true. Work done is an energy transfer. Work done is force divided by distance is a false statement, and you should be aware from previous videos that work done is force times distance moved. So before we start linking the two equations, we're going to do a little bit of revision. So work done is energy transferred. Whenever energy is transferred, work has been done. And the equation, as we've just said, is work done is force times distance moved. And I've put that into a triangle for you so you can use that later. And it's important to remember the units. So work done is joules because it's the energy transferred. Force, as always, is measured in newtons. And distance moved is measured in meters. Pause the video now, write down that equation, you're going to need it later. And one important thing to remember here is that the force and the distance must be in the same direction. So again, a little bit of revision here on kinetic energy. So kinetic energy is the energy of movement, so whenever something is moving it has kinetic energy. And the equation for that is half the mass times velocity squared. And again, units are really important. Kinetic energy is joules, the mass is always in kilograms, and velocity is always in meters per second. So because these two equations involve energy transfers and work done is an energy transfer, we can link kinetic energy to the force needed for that movement, and also the distance that things move. So we're going to work through an example for you. So if we have a car with a mass of 500 kilograms and it travels at 10 meters per second, the first thing we're going to do is work out its kinetic energy. So the first thing we do is plug that into the kinetic energy equation, and I'm just going to write down the triangle and we're going to plug in what we've already been told. Remember, as always with our triangles, we need to make sure that we have our divide line and this is our times line. So our kinetic energy equation just fits in here quite simply. Kinetic energy, half the mass times the velocity squared. So we were given in the question a mass of 500 kilograms, and we need half of that, so we're going to put half of that into our equation, so that's 250. And we were given 10 meters per second. So it was 10 meters per second, and that's our velocity, and we need to times that, but we need to make sure that we square it. 10 meters per second squared. If we plug that into our calculator, we will get 25,000 joules of energy. And so that's the first part of the question. So the next thing that they might do is ask you to link that to work done. And the sort of question they might ask you is, what is the braking force if the car stops in 10 meters? So we're now going to use the work done equation, and I'll show you now how we transfer this information across in order to work out the force used by the brakes. So what we do now is we're now going to put down the work done equation. And again, I'm going to use a triangle. So we have times line, divide line, work done equals force times distance. So we worked out previously that we have 25,000 joules of energy. So that's our kinetic energy. Now when a car stops, it will go from having 10 meters per second, it will go to 0 meters per second, which means its kinetic energy will then be 0, which means there's been an energy transfer of 25,000 joules, and we're assuming here that it's 100% transfer. So we can transfer that energy directly across to work done, because that's the amount of energy that was transferred. So here we have 25,000 joules, and we were given in the question that it stopped in 10 meters. So now all we need to do is rearrange that equation using the triangle. So we cover up the force, which leaves us with work done divided by distance, and we can just plug those numbers in. So the force is going to equal 25,000 joules divided by our 10 meters, which will give us 2,500 newtons. And that's how we link these two equations. So the only way to do these is to practice them. The only way to get good at them is to practice them. So there's a couple of questions there. I'd like to pause the video now and have a little go. First one just copies what we've just done, so have a little practice at that. And the second one is using the work equation twice through. So have a little go at that and see how you get on. Okay, so for the first question, again, the first thing we're going to do is put in our triangles. So we have the kinetic energy, remember divide line times line, half mass times velocity squared. We also need to link that in with the work equation. So again, we have work done equals force times distance. So the first part of the equation was the mass, and they gave us a mass of 800 kilograms. We need half of that, so we have 400. Okay, so half of that divided by 0.5 gives us 400. We had a velocity of 12. We need to square that, so we're going to have 12 squared. So we've got 400 times 12 squared, put that into the calculator, gives us a kinetic energy of 57,600 joules. So that's our kinetic energy. Now we're going to assume that when it's stopped, all of the kinetic energy has been transferred. And an energy transferred means that's the work done. So we've had work done of 57,600 joules. We were told that it stopped in 8 meters. So again, we cover up the force, we get work done divided by distance. So the force will equal 57,600 divided by 8, which gives us the force applied by the brakes of 7,200 newtons. So question 2, we're going to pick out what they've given us. So the first part of the question, they gave us weight, which equals 5,000 newtons. Remember, weight is a force. They gave us a height of 4 meters. Remember, height can also be used as a distance. And they've asked us for the work done. So we're just going to do the work done equation. I'm going to use my triangle again. So we have a force of 500 times by a distance of 4 meters. And that gives us an energy transfer, so work done, of 2,000 joules. Now on the next part of the question, they asked us how much kinetic energy it would have right at the end. Now, assuming that it's 100% transferred, then the answer to question B is just the whole of the energy being transferred, therefore it will be 2,000 joules. And in the second part of the question, they gave us a distance that the shoe was compressed by 0.01. Now again, we just need to use the work done equation. So we're going to start, so this is right at the end, we're going to start with the work done is going to be the amount of energy that was transferred, which was 2,000 joules, and force times distance. And we're looking, the distance they've given us now is 0.01. And they're looking for the force on the shoe. So again, we cover up the force, we've got work done divided by distance. So the force on the shoe for the compression would be 2,000 times 0.01, which will give us 200,000 newtons of force going into that trainer. So there's a summary of the answers to those two questions. Hopefully you found that useful. Make sure that you do plenty of practice, get some past papers and do plenty of practice at these linking of the equations. So I'm hoping now that you have an understanding of work done. You're able to use the work done equation, and also you're able to link kinetic energy to work done and do those linking calculations.